The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Well, I'm going to just to illustrate some point contained in the guidelines for the strengthening of masonry structures. This document was published by the National Research Council of Italy in 2004. It was the first edition. Then, 2 years later, it was translated in English and also with help of Tony Nanni. And we have a revised version that has been published in 2013. Now, of course, this is a result of a team, and I just coordinated the team. And now, more or less the same team is working in a new document concerning the guideline for the use of FRCM. Let's start with my presentation. All the document is based on several chapters, as you can see here, and the chapter number 5 concerns the strengthening of masonry structures. This is chapter 5, contains several sections. It is the outline of my presentation, more or less. I will not present any formula. I will just illustrate the content and the philosophy of the document. Of course, if somebody can be interested, the document can be downloaded free from the CNR-DT site. I will go from introduction to some design assumption. The problem of the bonding is very important. The evaluation of the safety for different kind of masonry walls and for arch and vaults. The problem of confinement and design for seismic application and so on. Let's start with some point in introduction. And the scope of the application of FRP is double. The first is to increase the capacity. The second, when possible, is to increase the ductility. That is very important, of course, in seismic zone. Of course, FRP are used for strengthening also historical and monumental buildings, but in this case, a very great attention must be done because the application must be justified and carefully detailed and should be in compliance with the theory of restoration, more or less. About the criteria for the design of the strengthening, we can apply the reinforcement on consolidated masonry, and the idea is that the FRP must work in tension and not in compression. About the structural modeling, we can use different models from nonlinear to linear and simplified model, and the nonlinear, which are the most difficult to use, have to be properly justified, of course. Failure mode is exactly the same that Gustavo illustrated. Tensile cracking for the masonry, tensile cracking, crushing compression, slip shear always for masonry, and FRP rupture and the bonding. The rupture typical for the coupling of masonry and FRP. Concerning the constitutive law for masonry and FRP, we can use this kind of constitutive law. That means we assume that masonry is a no-tension material with a limited compressive strength and also as a brittle failure when a typical strain is reached. On the FRP, we assume that it works mainly in tension and is a linear elastic behavior until a brittle failure. Concerning the FRP bond, it is a very important problem. The debonding is a very important problem because when the FRP is debonded, it does work. Moreover, generally this failure is very brittle and for this reason is undesired. There are several types of application of FRP and we give some formulas for this different kind of masonry in the document and for the end debonding and also for intermediate debonding. Another important point is the debonding for the application of FRP on carved structures, and is very important for carved structure when applied in the intrados of the structure because it's very easy that the debonding effect can arise. Then there is a section concerning the wall. The failure wall can be for out-plane failure or in-plane failure. Let's start with the out-plane failure. This is a typical overturning collapse. The FRP can be designed just making a simple equilibrium equation of this rigid body. Analogously, for vertical flexural bending, we can have this kind of mechanism that we have seen before. And also in this case, this is very similar to a picture that Gustavo presented also. We can find the right reinforcement just checking the bending moment required versus the bending moment that resists to the structure. Also, horizontal flexural failure is included in the document for this kind of mechanism. And in this case, we have an arch effect. And of course, also in this case, we can apply an external FRP that can be designed using typical formulas of the bending moment also in this case. Let's go to the in-plane case. Generally, we prefer that the FRP are applied to both sides, such that the application is symmetrical, and the check can be performed computing the resistant moment just considering classical formulas, the stress block, and so on. Of course, we cannot consider the presence of the FRP if you have no anchorage at the basis. So if we have the maximum moment here, we have to consider the presence of anchorage. About the shear capacity, we can apply horizontal FRP reinforcement, and in this case we can apply this kind of formula for the shear design, so that the resistant shear is the sum of two quantities, the shear absorbed by the masonry and one taken by the FRP contribution. And of course we have also the possibility that we have a different failure, that is the compression of the strut in truss. Then there is a section concerning single and double curvature structures, and well, the idea is that the collapse occur because of the opening of hinges, and FRP can prevent this opening of hinge. And of course we can see typical intervention that we can apply on this curved structure. We studied the case of arches, barrel vault, domes like the one we have seen before, and groin vault, so substantially. Just one word about the collapse. We can think that the collapse of an arch occurs by formation of hinges, and when this kind of mechanism occurs, we can apply, for instance, in the internal surface, we can apply an FRP. In this way, we avoid, inhibit the formation of this hinge, and analogously, we can apply an FRP on the external surface in order to avoid this opening. It is not preferred to apply FRP on the wall surface, internal or external, and also to both the two surfaces. Another point is that the application of FRP can inhibit the formation of the flexural hinges, but is not able to overcome the failure due to the shear. So in this case of collapse, FRP is ineffective. Then there is a section concerning the confinement of masonry column. It's a very standard formula. This coefficient is increased as a function of the confinement of the quantity of FRP wrapped around the column. Of course, we can have columns that are circular, but also polygonal, prismatic. So we have to compute the effective area that is compressed for FRP, or also introducing the bar inside. Design for seismic application, there are several points. Mainly, it is important the connection between the floor and the vertical element, between the vertical element, and so on. Another point very interesting is the installation and the construction detail. And finally, we present several examples of application, several examples of design. I just presented one. This is a facade with 3 openings and 4 columns, 4 piers. This is the scheme. vertical load and horizontal load due to seismic action, for instance. Here we can see the diagrams for axial force, shear forces, and bending moment. Then we can see that in this case the action, the bending moment required is greater than the bending moment resistant. So we have to make an intervention. And analogously, this is the pier number 1 and this is the pier number 2. Analogously here, the bending moment required is greater than the resistant bending moment. So, on the contrary, for panel 3 and 4, everything is okay. Here, the shear capacity, and for panel 3 and 4, no problem. For panel 1 and 2, again, we have a little problem here, and a bigger problem here in this part, where the shear capacity is lower than the required. So finally, this is the kind of intervention we proposed: vertical intervention for the bending moment and horizontal for shear. And finally, we start with all checks, and we find all checks verified, and we can also see which kind of failure could occur, and for the piers number 1 and for pier number 2. And for bending and shear capacity. Finally, that's all. And of course, I hope to collaborate with all of you now in this new document that we are starting to prepare for FRCM. That is very important for us, and I think it's very important mainly for masonry more than for concrete. Thank you for your attention.